In this video, we are going to study about the central limit theorem for proportions. Now, the goal is to use the central limit theorem to compute the probabilities for the sample proportions. So let's first define what is a sample proportion versus a population proportion. So we use the notation, the small letter p, to represent for the population proportion. And we use a symbol p hat, p with the hat notation, as a ratio of the x of the sample size n to represent for the sample proportion. So let's say, for example, you want to see how many people, what is the proportion of the number of the people in your city who own a dog. So it's very difficult for you to go out and ask every single person in the city to check on them to see if they has the dog or not. It's impossible to ask every single person. But we can select maybe 100 people just for a sample of 100 people, and then we ask them, all the people of that sample, and then it turns out that maybe 68 people who own the dog, and therefore 68 over 100 is the ratio of that sample of the people that have the dog, or the sample proportion should be 68 over 100. And 68 is the number of the x, and 100 is just the sample size of that sample inside a big population. And because every time that we conduct another 100 people, 100 other people, another different sample, we would get a different value for the p hat, because we would get a different answer for the x. Then therefore, the value of p hat is changing, and therefore p hat is another random variable of the sample proportion, and therefore it also has the sampling distribution of p hat, and the probability distribution of all the p hat value is called the sampling distribution of that p hat, or the sample proportions. And also from the last section, we also saw that the mean of all the sample proportion is approaching to the population proportion. However, the standard deviation is not. Remember, from the last section, we saw that only the sample mean, sample variance, and sample proportion, those are the unbiased estimators. That means they target to the value of the population parameters. And the standard deviation, they are not going to approach to the population standard deviation. Therefore, if you take the standard deviation of all the sample proportion, you are not getting to the same value of the standard deviation of the population proportion. And we get another different formula here. The square root of p multiply 1 minus p, and then over n. And the standard deviation is sometimes also called the standard error of the mean. So standard error of the mean. So they are the same thing, standard deviation or the standard error of the mean. So if you take a look at this figure, we can visualize that. You can think of this box is the big population. So we take each sample. This is a sample of the proportion p hat, maybe 100 for the sample size, and then we pick another 100 sample size. So of course, when we are picking 100 different values, the p hat, the proportion of that sample, of that particular sample, should be different. So each sample with the p hat, each of them they all have the different value of p hat. So p hat has a probability distribution because that is a random variables. And in this example, if we use a coin and we are flipping the coin between the head and the tail, now we can get the sample proportion of the heads after we are flipping the coins, and we can plot them on the probability distribution function distribution table. And then if we plot them, we would get a normal distribution for the curve, for the density curve. This is the normal distribution curve. And if I increase the sample proportion, if I increase the sample size, then I will get more and more approaching to this normal distribution of the histogram here. So this first figure is not approaching all the way, but then for the second one, we see that it's very approaching to all of the histogram, the value of the probabilities of all the sample proportion. So they are fitting very well to the normal curve in this case. And therefore now we are ready to talk about the central limit theorem for proportions. So we let p hat to be the sample proportion for a sample size n from a population with the population proportion p. And we have two requirements here. If n times p bigger than or equal to 10, and also n times 1 minus p is bigger than or equal to 10, then the distribution of the p hat, p hat again is a sample proportion, each of them, inside a big population. Then the distribution of those p hat is approximately normal. So if those two requirements are met, then the distribution of p hat has the curve that is approximately normal, as you can see from the last figure, is approaching to the normal curve. And I'm pretty sure that the two requirements are met for the second picture right here. That's why we have a very nice curve that is approaching to the normal curve. And we have the mean of all the sample proportion is approaching to the population proportion, and the standard deviation is not approaching to the same standard deviation of the proportion. But we have a slightly adjustment for that standard deviation formula of the sample proportion, which is the square root of p1 minus p over n. Remember, only the mean is the unbiased estimator. The standard deviation is not. Alright, let's take a look at this example. Okay. This is the first example. According to a Harris poll, chocolate is the favorite ice cream flavor for 27 of Americans. If a sample of 100 Americans is taken, what is the probability that the sample proportion of those who prefer chocolate is greater than 0.30? So first thing, we are talking about the sample proportion. So firstly, let's check the requirement. These two requirements. If we have those two requirements, we can then go ahead and use the normal distribution. In this case, n is the sample size, which is 100. P is the proportion, the population proportion. According to the poll, then chocolate is a favorite ice cream flavor for 27% of the Americans. So that is the proportion for the whole population of all Americans. So this is P, and 27 is 0.27 if you convert it back to decimal values. So n times P, this is bigger than 10. N times 1 minus P is also bigger than 10. So we are good to use the normal distribution for this problem. Okay? If we are using the normal distribution, we know that the mean is the unbiased estimator. So the mean of the sample proportion is approaching to the proportion of the population P, which is 0.27. However, the standard deviation of the sample proportion is not. It's equal to some adjustment here, the square root of P1 minus P over N. P1 minus P over N, which is 0.044396. And next thing, we are asked to check what is the probability that the sample proportion who preferred chocolate is bigger than 0.3. So we know that the proportion 0.27, that is the mean value, of the sample proportion. The mean is the middle value at the middle of the peak value, 0.27. Now we are looking for all the sample proportion bigger than 0.3. That means we are looking for 0.3 and all the way to the right. What is the area under this curve here? Okay. Firstly, I can still apply the standard normal distribution, but first I have to find the z-score. The z-score again, z-score from the last chapter, z-score equal x minus the mean divided by the standard deviation. In this case, we are talking about what? We are talking about the sample proportion. So we take that instead of the x value, and we minus for the mean of the sample proportion, and we divide by the standard deviation of the sample proportion. We got everything from above, and this is 0.3, and 0.3 corresponds to 0.68 on the z-scale. Okay, z-scale right here. So we are looking for the right area, and I can use the table. This is the positive z-score table. So I go ahead and I take out that. I'm looking for 0.68. This is again the area to the left side of that z-score. So 0.68, 0.6 is right here. We need another 0.08. So we go all the way to the right, which is this column. Right, this is 0.08. And I get 0.7517. That is the area to the left side, all of them to the left side. To the left. However, we are not looking for the left area, we are looking for the right area. And remember, the whole thing, everything has the area of 1. And if you want to look for this area, we take 1, we subtract whatever we got here, we will get whatever we have remain from the right side, which is 0.2483. Another example. Approximately 60% of eligible voters voted in the 2016 US presidential election. If a sample of 88 eligible voters were polled, would it be unusual if less than half of them had voted? So this is the type of the problem that we are considering about the proportion, the ratio. Okay? So we are checking to see if less than half of them has voted. So we are looking for the sample proportion, which is p hat So we're checking if p hat is really less than 0.5, because 0.5 is half. We want less than half, so it's less than 0.5. So now this is a sample proportion. For a sample proportion, we have two requirements. NP. N is the sample size. The sample size of 88 voters. So 88 is N. This is N. P is the proportion. This says that at least approximately 60% of eligible voters voted. So that is the proportion of the whole population during the 2016 US presidential election. So this is your P. And 60% is 0.6. So multiply that, you get 52.8. That is bigger than 10. So that's good. And then what? N times 1 minus P. And we also get a number which is bigger than 10. So these are the two good requirements. So we are okay to use a normal curve. So after we know it, we can apply the normal curve. We know that for the proportion, the mean mu is the mean of all the sample proportion will be approaching to the population proportion. And we got the p-value earlier, 0.6. So the mean of that is 0.6, the mean of the sample proportion. However, for the standard deviation is not. Standard deviation is the bias estimator. And therefore we use the formula square root. This is the central limit theorem for the sample proportion. P1 minus P over N, which is this value. And now we are looking for the question, would it be unusual if less than half of them sample proportion is less than 0.5? Alright, so we know that the mean is at 0.6 at the center. We are looking for less than 0.5. 0.5 is before 0.6, and then it's less than that, so all the way to the left side. Okay, this is what? This is the p-hat scale, sample proportion scale, not the z-score scale. I can do the z-score scale. I can use the z-score value. So first thing is the z-score is equal to the sample proportion minus the mean of sample proportion divided by the standard deviation. We got 0.5 because we are looking for that specific value. And then 0.6, right? We are converting 0.5. We are trying to convert 0.5. So 0.5 is the value of a sample proportion. So we put them here, minus the mean. The mean is right here. Standard deviation above, right here. So now I got minus 1.91. So that is the negative z-score. So now this is the z-score scale. 0 is at the center. This is the standard normal distribution. And we got a negative 1.91. Let's use the negative z-score table. 1.91. Negative 1. Negative 1.9 is right here. But they are looking for negative 1.91. So we need another 0.01. 0.01 is right here. So 0.0281. And that is the area to the left side of that. And fortunately, in this case, we are looking for the area to the left, so we don't have to do any more subtraction. So that is the answer. Okay, and this one here is the probability of getting a value inside this interval. And if you convert it back to 2 decimal places to get to the percentage, you will get 2.81%. This is less than 5% of the bottom 5%. So the answer should be unusual, right? The question asks you what? The question asks you, would it be unusual? So remember, if you find a probability and that probability is less than 5%, then that is considered to be unusual. Remember from the last chapter, we say that if anything inside the bottom 5% and the top 5%, we consider them to be unusual events. Now let's try to use the TI-84 to solve this problem. We can also use that. If we are using the TI-84, you do not need to convert it to the z-score. Let's do it here. So we go to the distribution. So second, vars. This is the normal curve. So we go to normal CDF. In this case, we are looking for this interval, this area. The lower bound is all the way to the left. It's a very small value to the left side, or negative infinity, and you can put something like negative 99999, 6 number 9. That is very large to the left side. That's good enough. And then the upper value, you want it to go up to 0.5, and then the mean here is 0.6, not 0. 0 is the standard normal distribution, and then the standard deviation, just right here, the standard deviation, so that is 0.05, so 0.052223, and then hit the enter. Or you can use a function normal CDF on TI-83 and then enter the lower bound, comma the upper bound, comma the mean, comma the standard deviation, and close everything and hit the enter. And then I would get the same thing, 0.2027. That should be the same thing here, 0.028. They round it up, but the calculators would give you the exact value. Okay, if we are using the Excel, you can also do that too. Let me show you that on Excel. Okay, so we can also find the normal CDF using the Excel as well. So on Excel, what we do now is we go to a cell, we hit the equal sign. This will prompt the Excel to give you return the answer at the end of the function. So what we do now is we go to the formula tab, formula, and go to insert function. Now there's a few of them here, but we should choose the one with statistical because we are studying statistics. And then just scroll down. We are using normal distribution, so we are looking for normal distribution. So NORM stand for normal, DIST distribution. Click OK, and then here, now go back to the question. The question is, you are looking to find the value of before, all the way from the left up to 0.5. So the X value is the ending point. This is where you want to stop at. So you want that to stop at 0.5. The mean is at 0.6. The center, the standard deviation, which is the one we got earlier, right here, which is 0.052223. Now, for the function, for the cumulative means if you want to add everything from the left all the way to the left up to 0.5, or you just want to compute the value at exactly 1 point of 0.5, because you want everything from all the way to the left, from the left to 0.5 to get the whole area. So the answer here is true. That is correct. So we type in the true, the logical value, and then you see that you get the answer at the end, 0.0277, which is what I got from the TI-84. Yeah, I got that. Same value, same thing. Okay. I'll click OK, and then it will return you the value that we got, the same, exactly the same thing. So the TI-84, the Excel, or the standard normal distribution, they all give you the same answer here, routed to the 4 decimal places. And remember, if anything less than 5% is considered to be unusual for the bottom 5% or the top 5%.